Okay, great. I'll start then with this story of principal specializations. So of course, our basic object is the symmetric Mcdonald polynomial. Which we denote as P lambda or P lambda QT if I want to stress the dependence on Q and T, or even P lambda x1 up to xn and Q and T, because there are n variables. And of course, the Schur function is a special case of this P lambda. The Schur function is denoted S lambda, which is P lambda of TT. So when you set Q equal to T, you get the Schur function. So this is some miracle that when you set Q equal to T, then the resulting polynomial has no Q's and T's anymore. Everything cancels and disappears. It's quite amazing. Okay, so well, I can go all the way back to the beginning when I was in graduate school. I thought this was the most amazing fact that I could imagine, was that this Schur function, which is defined just purely in terms of determinants, is equal to the character of L lambda. So L lambda is the irreducible integrable module, GLNC module of highest weight lambda. And then there is, so that means the fact that it's a character, that means that if you take the Schur function and you specialize all the variables to 1, then you get the dimension of this module. So I still find that just completely amazing, because a simple module is something which is nearly impossible to compute. I mean, in any example, if you try to compute simple modules, even for a 4-dimensional algebra, you have to do a lot of work somehow. And this, it was just a fact that you get this dimension. And then even more amazing is that there is some combinatorial formula for this, which is n plus the product over the boxes in the shape lambda, n plus the content of the box divided by the product of the hooks. So in our minds, lambda is some partition, and I will discuss these statistics carefully in a moment, what are content and hook, but just the fact that there's a formula, which is the product of some combinatorics, is for me amazing. So this is the dimension. So
n plus
yeah,
the content
of the box, sorry. Yeah, not lambda, the box, content of the box. Okay, so that's my dimension formula. And then you learn, especially if you look up Hermann Weyl, when he first discovered such formulas in general, what he did really is he took this principal specialization of the Schur function, or of the Weyl character, and that is something which is now called the quantum dimension. Many places in its role as a quantum dimension in terms of quantum groups and so on, modular tensor categories. And that, so what Hermann Weyl had understood was that in fact, it's this principal specialization has a combinatorial formula, which is 1 minus t to the n plus the content of the boxes divided by 1 minus t to the hook of the box. So again, if you just look at such formulas, this is just amazing, because here is something which is a priori some rational function in t. And the fact that well, even look at this is something which is a priori some rational number. And the fact that it's not a rational number, that is just an integer, is incredible. I mean, this is
what is q?
Sorry?
What is q, the right-hand side, whatever it is?
That's just a notation for quantum dimension. I mean, it comes from the people who work in tensor categories. They use this notation of quantum dimension, but it's just a notation. There's no q at the moment.
So it's just one word, QDIM, not.
That's right.
It's not Q.
That's right, QDIM. That's right. Okay, so these are somehow incredible. I mean, there are generalizations, vast generalizations of binomial coefficients. If you teach in your first combinatorial class, you teach binomial coefficients, and then it's a miracle, again, that n factorial divided by k factorial times n minus k factorial is actually an integer. So, of course, all right. So there is a passage, of course, Hermann Weyl realized that this was how he obtained the dimension formula, is that he took the limit as t goes to 1 of the quantum dimension, and that produced the dimension. Okay, so now is the miracle which I want to talk about today, and that is if I take p lambda and I take the principal specialization, so this also has a product formula. So this is, oh, I forgot the factor, sorry. Now I look at my notes, there's a factor here, t to the n of lambda. And so this has also t to the n of lambda. And now it's the product over the boxes. And it's 1 minus q to the coarm t to the n minus the coleg divided by q to the arm of the box t to the leg of the box plus 1. So I would like to call this one, well, there are many reasons to call this an elliptic dimension. So I mean, more and more we are starting to learn that in fact there is such a thing as elliptic representation theory. And somehow the elliptic dimension of this L lambda, we might even write dim of L lambda. And somehow this principal specialization of the Mcdonald polynomial is trying to be the elliptic dimension. And there is, of course, a passage here, which is when you set q equal to t, then the Mcdonald polynomial becomes the Schur function. And so this takes the elliptic dimension to the quantum dimension, and then you proceed this way. So I find this formula completely amazing. And I have to say that my whole life, in some sense, has been trying to understand these constants, this content and this hook length. I just try, what do they mean? What do they mean in terms of representation theory and so on? So let me remind you what these statistics are, and then we can think about what they mean. So we have a partition here.
Sir, what is n lambda?
Yeah, let me explain here. Let me tell you. So I have a box, and this box is in some row and some column. And these four lengths are these coarm and coleg. So coleg of lambda of this box is the row minus 1. And the coarm of the box is the column minus 1. And the arm of the box is the length of the rth row minus the column number. So this is the arm here. This is the arm length. And the leg of the box is r minus 1. So this is the leg length here. And n of lambda is equal to the sum I going from 1 to n of I minus 1 lambda I. So 1 up to lambda n of the rows, lambda 1, lambda 2, up to lambda n are the lengths of the rows. So something I said wrong here. This leg is lambda c prime minus r. So lambda 1 up to lambda n are lengths of the rows, and lambda 1 dash, lambda 2 dash, and so on are lengths of the columns. Okay, so that's what all of these statistics are: co-arm and co-leg and arm and leg and so on. So of course, what I had wanted to understand was this content and this hook. But now, of course, we have some hint of what that is, because the content of the box is, well, we can look just at the formula here. This numerator has to turn into the content when you set q equal to t. So the content is the co-arm minus the co-arm plus the co-leg. No, I had it right before. Co-arm minus the co-leg. So that's the content of the box B. And if you do representation theory of the symmetric group, these are amazing numbers because these are the eigenvalues of Murphy elements. So these I thought I had understood the meaning of them until I saw that the content should not be considered just as a content. It should be considered as a co-arm minus a co-leg. And now I have to rethink all of my past theory. And the hook length, so the hook length of the box. So again, we can put q equal to t, and we can see that the hook length is equal to the arm plus the leg plus 1. All right, so I was hoping that this would help to understand these mysterious statistics, these numbers. Okay, so now we have a general theorem. This is a theorem which is due to Mcdonald. So this is the theorem of principal specialization, and I'll state in general. So the first part of the theorem says that if I want to take the principal specialization, so I'm going to write in root system notation for a moment, of the non-symmetric Mcdonald polynomial. So there are two statements. There is principal specialization of the symmetric Mcdonald polynomial, and there is principal specialization of the non-symmetric. And amazingly, they both have nice formulas. So the first one, the symmetric Mcdonald polynomial, is the evaluation at minus k rho of c t lambda of y inverse. So again, I have not told you what these things are. What I want for the moment is I want you to be amazed at how simple the formula is. And it will reduce to the previous case. So, and then we will learn that these components in this formula, these are actually really fundamental objects. So this one is t to the minus 1/2 the length of V mu inverse, which you might remember is some permutation that's associated to the Mcdonald polynomial, and then evaluation at k rho of, again, a C function here at Y inverse. Okay, so let me explain the parts of this general theorem slowly. So first, let me make a remark is that for GLN, this element rho check is, well, let me write minus rho check is the vector, which is minus n minus 1 on 2, minus n minus 3 on 2, and so on all the way up to n minus 1 on 2. So this is sometimes written as the half sum of the positive roots. But let's write this a slightly different way. This is minus n minus 1 on 2 times the vector 1, 1, 1, 1 plus the vector 0, 1, 2 up to n minus 1. So this is the vector which in Mcdonald's book is called delta. 1, 1, 1.
Sorry, there should be a minus sign just above half sum of the roots.
A minus sign, yes. Thank you. Okay, so this rho check is something which is one of the big mysteries of Lie theory, if you like. But we can see that the crucial point for this vector here, because if you look in Mcdonald's book, what he writes is, well, let me write the formula, is that evaluation of minus k rho check of E mu is equal to t to the minus n minus 1 on 2 to the length of mu, to the size of mu, E mu evaluated at t to the 0, t to the 1, t to the n minus 1. Okay, so the purpose of this is to make contact with Mcdonald's book. So this thing you would see in Mcdonald's book, this type of thing. Book. It is symmetric functions book. Well, let me write the same formula for the p lambdas. So again, this is t to the minus n minus 1 on 2 times the weight of lambda, p lambda of 1 t squared. And so you might ask, why does he evaluate in his book, why does he evaluate at this strange 0, 1, 2? And this strange 0, 1, 2 is really some shift of rho check. So in fact, you can see that this lambda, this is the sum of the lambda I going from 1 to n, which another way to write it is that it's the inner product of lambda 1 up to lambda n with this 1, 1, 1. All right. Okay, so why did I say all this? Just to make contact between my formulas for principal specialization and Mcdonald's, the way of writing it in Mcdonald's book, and for another reason, and that is that we can see here that well, now you can do just a small calculation which shows that this n of lambda is actually equal to n minus 1 on 2 times the weight of lambda minus of lambda. All right, so I have put now all the things in place that you can easily do the calculation. Is that this is rho check, this is the difference, and in fact this crazy constant n of lambda, which is always seems so mysterious, is actually not so mysterious, because you can really see it's built from the two parts. one part is this 1, 1, 1, 1, 1, and the other part is this. This row check. Okay. And I'm going to write more formula for this, which will come up in a moment. So this is the length of T lambda. So in fact, here is the T lambda, and you may have noticed before that here also is a T lambda. So in both places, I have a T lambda. So this T lambda, whatever T lambda is, it somehow is trying to explain these crazy combinatorial constants. Okay, let me go back to this. So I want to try to understand this formula. I want to continue to explain this formula. Let's put it here for reference. Okay, so that's the. So in order to do that, it turns out I need to talk about the roots. So everything of this combinatorics, I'm finally starting to see it in terms of roots and inversions and C functions, which I think are really the fundamental structures. So we already saw sometime the affine Weyl group. So the affine Weyl group for GLN is bijections W from Z to Z such that they're periodic. So these are called n-periodic permutations. And n-periodic permutations are the affine Weyl group for type GLN. And of course, the ordinary permutations are bijections W from 1 through n to 1 through n. And so if I give you an ordinary permutation, you can automatically extend it to a periodic permutation just by using the periodicity. And so the ordinary permutations are contained inside the affine Weyl groups. Now, one of the first things you learn in symmetric group is that the inversion set is going to be of importance. So the inversion set consists of all roots so a root is a pair of numbers. So I will be between 1 and n, and k is an integer. And I should be less than k, and wi should be greater than wk. So that's called an inversion. And inversion sets are, so in particular, the length of a permutation is the number of inversions of the permutation, and the same for the affine Weyl group. Right? So you cannot work on permutation combinatorics without doing inversions pretty quickly. So these we feel like are something we should learn. Now there's an alternative notation which I think is powerful, so I want to use it for roots. And that is that, so beta check, so I have written IK here, IK, a pair IK, which is very common. So a pair IK is really IJ plus LN. Because this K is some integer which is bigger than I. So the K, it may be bigger than N, but I always want to write it as a pair where I and J are both in 1 to N, and then I can add some amount of N to keep track of it. And this notation is useful because then this in root system notation is epsilon I minus epsilon J plus LK, or I would often write this as LK plus alpha ij. All right, so even if you don't want to do Lie theory, you don't have to do Lie theory, but you will start to discover the parts of Lie theory. So this is what's the central extension for an affine Kac-Moody Lie algebra and the roots. So we can do pure combinatorics and at the same time we get good at this game. Okay, now let's define the C function. So if I have a root beta check, the C function, which I call C beta of y, and this is t to the minus a half minus t to the 1/2 y to the beta check divided by 1 minus y to the beta check. Or we could write that out more combinatorially, if you like. This is q to the minus L. So I'm thinking of my beta check here is of this form. So there's an L here, q to the minus L. And then yi, yj inverse. So those come from this epsilon I minus epsilon j. And divided by 1 minus q to the minus L yi yj inverse. All right, so this is called the Harishchandra C function. And because it was discovered by Harishchandra in his work on representation in the 50s. Amazing. It's if you ever get a chance to read those early papers of Harishchandra, it's really just amazing how he put his fingers on this combinatorial structure, which is okay. So this is what the C function is. And if I have a permutation or any element of the affine vowel group, I can just take the product over the inversion set of the C beta checks. So let's see if we can review slightly our components here. So we have these periodic permutations, and the periodic permutation has an inversion set, and we can build a C function for that periodic permutation just by taking the product of the C functions for the individual inversions. Okay, what I want to stress here is product. If there's anything which I'm trying to impress on you today, it's product. All right. Everything in this amazing formula, which we are looking at here, this amazing formula is right here a product. And this is the factorization which is happening in this. Okay, so we need one piece which I haven't told you, and that is that evaluation of minus k rho on this LK plus alpha ji is equal to q to the L t to the j minus I. Okay, so what does it mean? You don't have to parse all the i's and the j's and so on. What it means is that this y to the beta, this evaluation, it takes a y and it reduces it to a power of q and t. So this y to the beta here is going to reduce. And what is it going to become? It's going to become a power of q and t. So I'm exactly trying to get this principal specialization, and this evaluation is going to give me the power of q and t from the C function. So the C function is going to just spit out these powers of q's and t's. All right, so I hope that...
Arun, so in this formula for CW in the product, I guess the y's commute, and so it doesn't matter in which order you.
That's right. The y's completely commute. This is all sitting inside of rational functions in the y's. That's right.
Okay.
Yeah. Okay. So in my formula, which I have here, I have told you most of the parts. Except for, I haven't not yet told you what is this T lambda. So let me tell you what this T lambda is. So whenever I have any sequence of positive integers, in fact, that for that matter, they could just be a sequence of n integers, then you define a periodic permutation. So this is a periodic permutation. And you do it simply by setting T mu of I to be equal to I plus n mu I for I in 1 through n. So remember that a periodic permutation is determined by its values on 1 through n because it's periodic. So I can always compute the other values just from this one. And we don't do anything. We leave I is equal to I, except we shift it according to mu. So this is simply a translation in the this element T mu. Okay, so now I have T mu, and I can look at, yeah, I think I'll skip the u mu and the v mu because we don't really need them for today. So I can look at T lambda. So now I want to go to this symmetric Mcdonald polynomial. So I remind you that lambda is a partition. So this I'm thinking of now as positive integers with lambda 1, lambda 2, all decreasing. All right. So now you can just look. I mean, this is the kind of thing you give to your undergraduate students. You look at this permutation, T lambda, and you compute its inversions. So what are the pairs ij which get switched by this T? And when you do that, you do the homework assignment for your whatever second year combinatorics class or something, and you will find that these are exactly the pairs ij plus ln. This is not difficult. So I and j here are between 1 and n, and I will be less than j, and L will run between 0 and lambda I minus lambda j minus 1. Yeah, that's right. Okay, so this is yeah. Let's do the example so we can see. So here's an example. Is lambda equal to 5, 4, 4, 3, 2. So that means that I have 5 boxes in the first row, 4 boxes in the second row, 3 boxes in the third row, 4 boxes in the third row, 3 boxes in the fourth row, and 2 boxes in the fifth row. Okay, now I'm going to write my inversions. So I'm looking for pairs I less than j, and L has to run between 0 and lambda I minus lambda j minus 1. So So I look here at this pair. The first, this is lambda 1, and then I have lambda 1 minus lambda 2, lambda 1 minus lambda 3, lambda 1 minus lambda 4, lambda 1 minus lambda 5, and that gives me 4 roots, which I'll write as alpha 1, 5, alpha 1, 4, alpha 1, 3, alpha 1, 2. But in fact, if I look at 1, 5, the difference is 3. So I get here also k plus alpha 1, 5 and 2k plus alpha 1, 5. So that the L runs between 0 and lambda I minus lambda j minus 1. So the difference is 3, so I get 3 of these. And for 1, 4, the difference is 2, so I get 2 of these, alpha 1, 4 plus k. And for 3, the difference is 1, so I just get 1. And for 2, the difference is 1, so I just get 1. All right, so in this way, I can quickly fill up this diagram with all the roots, and you get alpha 2, 5, alpha 2, 4, alpha 2, 5 plus k, alpha 3, 5, alpha 3, 4, and alpha 3, 5 plus k, and alpha 4, 5. And so this is a picture of the inversions of T lambda. So this is, I'm just trying to do it in a concrete example. I have a very specific permutation, periodic permutation, and I want to compute its inversions because I'm trying to compute the principal specialization. And I can very quickly give a nice combinatorial form for the inversions of this periodic permutation. Okay, so now let's remember what our formula was, which we're trying to compute here. We're trying to compute this thing. And so that means that we're going to have to take here, we're going to have to take this C function and evaluate it. So let me look, for example, let's just look at one box and let's look at the C functions for that box. So if I look at, so consider box 1b equal to 1, 4. So that means I have to do evaluation minus k rho, and then I'll have the C function of k plus alpha 1, 5 at y inverse times the C function of k plus alpha 1, 4 at y inverse. And now I can just start to compute. This is equal to the evaluation of minus k rho, and you plug in your C functions, you get t to the minus a half, t to the half, you get y to the minus k plus alpha 1, 5, divided by 1 minus y to the minus k plus alpha 1, 5, and then t to the half minus t to the half, y to the minus k plus alpha 1, 4, divided by 1 minus y to the minus k plus alpha 1, 4. Okay. And then you can pull out 2 factors of t to the minus a half times 2, and then you get this, let's write this as evaluation of minus k rho, because just so you can see where the factors are coming from. So there's a 1 minus t, then this y to the minus k, this k, that y to the minus k is turning into q, And then you have y to the alpha 1, 5. Alpha 1, 5. And then again, you have 1 minus t, q, y to the minus k is turning into q, and then you have y to the alpha 1, 4. And so you have y to the alpha 1, 4. And then you get, so this turns into 1 minus t q to the t times 5 minus 1, because of this 5, this 1, 5, divided by 1 minus t qt to the 5 minus 1, and then my t to the 4 minus 1, and 1 minus qt to the 4 minus 1. And a miracle happens, because this cancels with that. All right. So what happens is that each box, so I had one box that had two roots in it, alpha 1, 5, and another, and alpha 1, 4. And that gives me a box that has one rational function in it, which is 1 minus qt to the 5 minus 2 divided by 1 minus qt to the 4 minus 1. All right, so each box, so the point is that each box, so I'm ignoring right at the moment this original initial factor, but each box gives one factor of this form. Of this, okay. So I had this example here. We can just do it. We can fill in the boxes here. So this box here is going to give me one factor, which is 1 minus q to the 0 t to the 5 minus 2 divided by 1 minus q to the 0 t to the 2 minus 1. And you can just read that off, because this last root is 2, 1, and this first root is 5, 1. So this is where these two exponents come from. And we can do the next one as well. So this box, it's going to give me a factor of 1 minus q to the 1 t to the 5 minus 2 divided by 1 minus q to the 1 t to the 4 minus 1.
Sorry,
So,
Arun, I think the numerator is wrong, because otherwise this will cancel. These two will. I think it's t to the 6 minus 1. If you go up to your example that you just computed, it's not 5 minus 2, because otherwise these two will cancel out.
no, I think,
This is,
So-
I mean, there's a
so-
tq t to the 5 minus 1s. So that's t to the
Yeah.
6 minus 1, not 5 minus 2.
oh, yes. Yes, you're right.
Otherwise
Yes,
they will
thank
cancel out.
you. Well, it's okay. Sometimes they do cancel, but you are right that I made an error. So 5 minus 0. How's that? Is 5 minus 0
Yes,
okay?
that's okay. That's right.
Okay. But so yes, you are absolutely right. So this should be 5 minus 0 in both places. And similarly here, you get 1 minus q squared t to the 5 minus 0 divided by 1 minus q squared t to the 5 minus 1. And in my mind, this numerator is always the first root in the box, and this denominator is always the last root in the box. This will be an important statement for me, is numerator is the first root. Let's see if we can somehow mark it, is that the numerator corresponds to the first root in the box, and the denominator corresponds to the last root in the box. Okay. Okay, so I filled in the other boxes because I was worried that it would take too long. So hopefully, if you do the same conversions for each box, you'll get what I have written here in this way. And now we want to go to the next step. So in the next step, what have I done is, you see these three numerator factors. These are the same as these three numerator factors. Okay, so I have just taken 1 minus q to the 0, t to the 5 minus 0, and moved it to the left. And then I have taken 1 minus q to the 1, t to the 5 minus 0, and moved it to the next spot to the left. And so on, I move that to the next spot to the left. And of course, I just put ones. And the denominator, we leave it exactly as it was. So it doesn't move any place. Similarly, here we take these two factors in the second row, and we move them to the left. So the two factors in the numerator of the second row, they move to the left of the second row. All right. And we do, in this way, we have not changed anything, so I can certainly put an equals sign here, equals. I'm just computing. Remember, what I'm doing is I'm computing this product of this, we are computing this formula here for the principalization. So that's what this is doing for us. And at the moment, all of these C functions, we are tracking them one by one in these boxes. We're keeping track of them. Okay, so now I can fill in these factors here. You see there's a pattern here that this is, let's see if I put them in red. This is q to the 0, q to the 1, q to the 2, and it's always the same numerator. So let's fill in, yeah, 1 minus q to the 3, t to the 5 minus 0, and 1 minus q to the 4, t to the 5 minus 0. All right, so I put in some extra factors. Of course, I better also get rid of them. So I'll put here 1 minus q to the 4, t to the 4 plus 1. Why did I, so of course, I hope you agree that this factor cancels with this factor. But why did I write 4 plus 1 instead of 5 minus 0? Well, because there are 4 boxes below this one. So this 4 plus 1 will cancel with that, but these are exactly these 4 boxes. And similarly, you put here 1 minus q to the 3, t to the 4 plus 1, and that cancels exactly with this. So I'm not changing anything. Everything is still equal. You can fill in one by one all of these things, and that's exactly what I did. Is I filled in, these cancel with these two terms, and then these two terms, they cancel with these two terms to leave me what I had before. And then these two terms, they cancel with these two terms. And which takes care of the ones that I had before. And then the same thing here. This term cancels with this term to take care of those two. And this empty box is filled with 1. Because the numerator and the denominator, they both cancel each other. And similarly, this box, well, now here I think I have it. Is this, this is not right here.
You're extrapolating from the boxes above in the same column, right? For each of the cells, and they cancel
Yeah,
each other.
but this should be a 0 plus 1. This should be a 0 plus 1. And then I get a cancellation like this.
Right. Yeah.
Okay. All right. But now this is exactly, if you look at this expression, this is exactly the product over the boxes in lambda of 1 minus q to the co-arm t to the n minus the co-leg divided by 1 minus q to the arm t to the leg plus 1.
Okay.
In every spot, it's exactly those numbers. So in fact, this arm and this leg, these are exactly these denominators. And these denominators are exactly this last root. So the last root in each box is the hook length. It really is a root of an inversion of a permutation. And that's somehow the meaning of the hook length. And this numerator, this content here, so that's this numerator, and that numerator came from the first root in each box. So in this Weyl, in this Weyl dimension formula, this elliptic Weyl dimension formula, we have now discovered what each of the parts of the formula is in terms of the inversions of this element T lambda. So let me write a statement. So this explains the statistics in terms of the inversions of the n-periodic permutation. T lambda. And I think that's amazing. For me, that's the best discovery of the semester, because somehow these statistics I have been trying to understand where they come from a long, long time. And I think we are finally learning that, in fact, Hermann Weyl was doing affine Weyl group. He just didn't know it. Everything is in the affine Weyl group. Okay.
Sorry, I have a question, sir.
Yeah.
Yeah, so for filling in the denominator in the first box, you put t to the power 4 plus 1 because looking at since there are 4 boxes below that, right? The first column.
Yeah. So 4 plus 1.
So what?
This is the leg. So this length is this leg.
Yeah,
So,
but what happens if this lambda 1 prime is not large enough? Say lambda 1, the number of boxes in the first row, this is quite large. So you need to give more higher powers of t, but you have less number of boxes in the first column. Then you have to incur some minus sign, right? And will the formula match?
No, but no matter where I want to do it, will always be the leg of it, the number of boxes below. If there is a miracle, the miracle is that this cancels with that. You know, that's where the miracle is. But being able to fill it is just this number, so there will never be a problem filling it.
Yeah, but basically this 4 plus 1 has also basically this number has also come with the power of t, which you basically filled in for the rightmost box, right? They have to match, otherwise they will not cancel. Q to the power 4, p to the power 5 minus 0. So if you have more boxes in the first row but less number of boxes in the first column,
It will never happen. The theorem is that they cancel.
Oh, okay.
That's the theorem, is that this number here will exactly cancel this number. So, yeah.
Thanks.
It's a mirror. It's amazing. This combinatorics is truly amazing. So I will agree with you that it's shocking, but it will never happen. It will never mess up. It will never be wrong. Yeah.
Not magic exactly, but almost magic. Exactly.
I think our job as mathematicians somehow is to make it less magical, or to find a way to.
I mean, I think, yeah, you explained it. Yeah, you demystified it in some sense. So thank you for that.
Yeah, partly, but there are many questions that are still in the background. For example, this row, I keep saying that this row or this sequence, you know, why is it so fundamental? If I were going to make a remark on that, this is maybe a little bit more advanced, but rho is the Jacobson-Morozov semi-simple. Morozov semi-simple. Corresponding to the regular nilpotent. You see, why should this formula is just too amazing? Why should it work? You specialize this p lambda at some special values. How did you know where you should specialize it? I mean, I could have chosen anything. I could have chosen 6, 5, 3 and specialized the variables at those. But no, I specialized it at some very special place, and then I get a beautiful factorization. So it becomes very important to ask, what is the role of this row? Now, I believe that the role of this row is somehow related to this regular nilpotent. But this is some part of the mystery which I cannot address. I don't, this is just some belief that I have, but I have no justification, no grounding for it.
Right, you want to evaluate somehow the character of a very specific element.
That's right.
By the way, actually, in this regard, I had a question at the very beginning. It's pretty much the next or related to this question itself. So if you go back to the beginning, I mean, it's the same question probably, but in the different, yeah. For the next page probably. Yeah, that. So the first line of the second page, yeah. My question was basically exactly that. If instead of like, why is the t equal to the t there? But maybe it's the same question. Like, is there anything known if you take some other u,
some other q?
No, some other u, like for the x's, if you take the powers of some other variable, or maybe for q or something like q times t, or is there something? Are there any other values for which something is known, a nice formula comes out?
No, I don't know any other values that are not somehow trivially related to this one. You know, of course, I could multiply all of these by 5, and then it's a factor that I can track because this is a homogeneous polynomial of a certain degree.
Right.
But it's amazing because even if you take these in reverse order, for the p lambda, it doesn't matter. But for the e lambda, so we have stated for this, so maybe I should say another fact, which is in my head. So I actually have 3 such formulas. So you might remember I had some fermionic Mcdonald polynomials as well. And those you can also principally specialize. You specialize at the same place and you get 0. Okay, so the principal specialization of a fermionic Mcdonald polynomial is 0. However, if you reverse the order of the variables here, which is the same as replacing this minus k rho by plus k rho, it does not specialize to anything nice. So let me just say it this way: evaluation of positive k rho check of A lambda plus delta is horrible. It seems to have no meaning. Of course, you see, for this P lambda is symmetric. So the positive row check and negative row check, they are related to each other by W naught and a dual element. So so positive row check for P lambda still does have a good factorization, but for another reason. But if you take positive row check for either of these others, you get garbage. So it's very, very sensitive to the row. Yeah.
Yeah, thanks. Venkatesh, are you here?
Yeah, you were talking about this elliptic representation. Can you explain what it is actually?
Well, I don't think anybody really knows, but I can say, well, I can just put a new page here. Let's go back to this place and let me put a new page. So so let's see if I can say it. All right, so let's just remember a little bit of Borel-Weibot, and I'll try to make the connection here. So Borel-Weibot says that if you take the flag variety, so G mod B is a flag variety, and associated to lambda, you take L lambda is a homogeneous line bundle corresponding to a character of the, so it's a line bundle on G. G mod B, on G mod B. And Borel-Weibot says that L of lambda, the irreducible representation, which we are computing the dimension of, so I'm not going too far away, it may seem, is the global sections of this line bundle. All right, so this is very closely related to this dimension question. And then the hierarchical homology vanishes. So HI of this, provided the lambda is a partition, is dominant, then this is 0 for I bigger than 0. Okay, that means that if you try to take an Euler characteristic of these guys, then all you see is the 0th cohomology. Right? But you need to, so what you want to remember here is that this Euler characteristic is the push forward of this line bundle to a point. So let me write that a little bit better, is maybe I should write shriek to be, is that I'm taking something in the K theory of G mod B, a line bundle is a vector bundle on G mod B, and I'm pushing it to the K theory of a point. And if I take T equivariant K theory, I keep torus, and this goes exactly to that sure function. All right, so this is this character of this line, of this L lambda. All right, so you can recover the sure function and these dimension formulas in terms of the geometry in this way. So I didn't talk at all about geometry, but you can think of all of these product formulas in terms of Euler classes on this flag variety. Okay, so now let's take the elliptic cohomology of this. Instead of K theory, we take elliptic cohomology. And again, we play the same game. And we try to take the line bundle and we push it to the point by pi shriek in elliptic cohomology. And what is amazing is that you start to recover. Now this elliptic curve has a Q in it, as well as the torus that we've had before. So remember that the row check is sitting inside of this torus. So, and that's where the T's are essentially coming from. But the elliptic curve is built from C modulo a lattice. So this is my elliptic curve. And Q is e to the 2 pi tau. All right. So here you get something. And actually, Nora Ganter has proved that this is essentially the Weil-Katz character formula. Katz character for the affine Lie algebra. This is the result of Nora Ganter. Okay, so the point that I'm trying to say things which we don't really understand, but somehow this elliptic cohomology is picking up now the affine. And even from the combinatorial point of view, I was trying to say that this new dimension formula is picking up the affine Weil group. What is the source of this affine Weil group? Where did it come from? Before we had no affine sure function, it seems that we have no affine Weil group. Everything is finite geometry. But as soon as we add to the finite geometry, it's the same geometry. As soon as we add the elliptic, then we get the affine. So somehow there is more and more evidence that these kinds of constructions should produce elliptic versions of Borel-Weber, elliptic versions of Weil dimension formulas, elliptic versions of everything you hope to get by somehow attaching your data again to this elliptic curve. But I don't really know anything. It's all philosophy at this point.
Okay, but taking like so from the affine Lie algebra modules. Okay, I don't see immediately like any way to get to the L of lambda.
No, yeah, I mean, are you asking how to go backwards? So somehow the source of it seems to be this line bundle.
Okay.
In both cases. And it's all about how you process that line bundle.
Any more questions or comments? If not, let's thank Arun Rao.
Right.
So this is his last talk, and we are at the end of this workshop. So at this moment, I would like to thank all the speakers and of course all the participants who made it actually this workshop success. So let's thank all the speakers and
Yeah. And especially thank you to, well, especially to Venkatesh, but all of the organizers who were working, putting the tutorials, everything. Great, it was great work. It was a pleasure for me.